In this section, we'll try to prove that objects move with respect to space itself, that time dilation effects are dependent on the observer's speed in space. This is not very difficult to prove, but it is not a popular concept in the scientific community. Just follow along. Corroborating evidence will be provided as we go. Let's start by quickly reviewing the concept of relative motion. Special relativity states that two observers in motion relative to each other perceive each other as running on a slower clock than their own, and that they experience some length contraction in the direction of motion. Let's use a real-life example to better illustrate the case. By some estimates, 10,000 muons fall to every square meter of Earth's surface every minute. Muons are created when cosmic rays strike molecules in the upper atmosphere. They have a very short life, about 2.2 microseconds. See this illustration for the path of a muon. Since muons are traveling very fast, near the speed of light, a muon experiences time dilation that allows it to travel much farther than the 660 meters that light would travel in 2.2 microseconds. Muons actually make it to Earth's surface, and well below, because they interact very little with other matter. That means that the life of a muon may be lengthened to about 500 microseconds. From the muon's perspective, Earth is moving at nearly the speed of light. Earth experiences length contraction and looks like a flat pancake. Earth's atmosphere is only a few hundred meters thick. A muon's 2.2 microsecond life is long enough for it to go through before it decays. These are logical-sounding explanations from the perspectives of the muon and Earth as to how events unfold. Let's introduce a third element to this event. Say there is a pulsar some 1,000 light-years away to act as a sort of clock. Let's have this pulsar send out a pulse every 100 microseconds. A real pulsar with a period that short cannot be found, but let's assume that one exists. Let's also have the muon's motion be perpendicular to the direction of the pulses. This will allow it to experience the same Doppler effect as Earth. Now, from the Earth's perspective, as the muon falls through the atmosphere, an Earth observer will see 5 pulses from the pulsar before the muon decays 500 microseconds later. From the muon's perspective, as it goes through Earth's atmosphere, it will also see 5 pulses in its 2.2 microsecond life. While Earth is seeing 100 microsecond pulses, the muon will see very short pulses, of only 0.44 microseconds. It is clear that the Earth's clock and the muon's clock are not running at the same rate when it comes to measuring the pulsar period. They are experiencing different time dilation effects, and since their time dilation effects are due to their respective speeds, we have to ask, speeds relative to what? Let's have another muon 180 degrees from the first on the other side of Earth, also moving near the speed of light and with about the same life as the first. The second muon's path will also be as long as the first, and it will see the same short pulse periods as the first muon. There has to be a speed along the axis formed by the two muons for which the perceived period of the pulsar will be at a maximum. A spaceship moving with constant acceleration along this axis will also see shorter and shorter periods for the pulsar as it approaches the same frame of reference as either of the two muons. This graph shows the period of the pulsar as seen by an observer depending on his or her velocity in space. The graph uses Lorentz's transformation equation to calculate the pulsar period as seen by a moving observer. For an observer on Earth, where the motion is relatively small, the period of the pulsar is very close to the maximum. There are many other cases where time dilation also works asymmetrically. For example, atomic clocks in orbit in the space station are known to run slower than atomic clocks on the ground. In this case, both the observer on Earth and the space station observer concur that the clocks on the space station run slower. There are some claims that the reason is because the space station clock is in a periodic motion, a recurring event as the station orbits Earth. We will see later on how these explanations fall short. First, we need to lay some groundwork.